Hello, everybody. It should be good morning, good afternoon, good evening. And today, let me first tell you that there will be two talks. The first one will be now, and our speaker is Professor Marcelo Aguiar from Cornell University in the United States. And then there will be a second talk at 2 p.m. local time, Brazilian time, by the talk will be by Irina Kashuba from the University of Sao Paulo. But first, let us go with the talk by Professor Aguiar. He is going to talk about Lie theory relative to a hyperplane arrangement.
Okay.
Professor Marcel, we have the floor.
Thank you. Thanks everybody for coming, and sorry for my failure to show up at the correct time last time. So can you hear me well?
Quite well. Perfect.
Okay, good. So this talk will be mainly about algebraic and mainly combinatorial aspects of free Lie algebras, and that's where we're going to go. It is from work in collaboration with Swapneel Mahajan, who's been a long co-author of mine and who is in Mumbai. So I'm going to spend a few minutes reviewing basic background on free Lie algebras that may not be necessary for the audience of this particular seminar, but to an extent is background that we need for the rest of the talk. So let's state the first basic definition, the two vector spaces that we want to look at. This is, of course, the usual commutator bracket between two elements in an associative algebra. And what I want to do is the following. I want to fix n variables, let's say n algebraically independent elements in an associative algebra, x1 through xn. And out of those n elements, I'm going to build two vector subspaces. One denoted by pair n. Pair refers to permutations, is a vector subspace spanned by a bunch of elements indexed by permutations of the n letters. What we do simply is to list them in a particular order, so choose a permutation and take the product of the n variables in that order. So in each of these monomials, each variable appears exactly once. So we have n factorial monomials, and we simply look at the vector subspace inside our algebra spanned by those n factorial elements, which of course are linearly independent because I am assuming that the variables are algebraically independent. So we have this vector subspace of dimension n factorial in which we're going to work. We want to look at this particular subspace of the space that we just defined, which is spanned by, well, all full bracketings of the n variables. So this is what I mean by a full bracketing. For example, when n is 3, what I have to do is, first of all, again, I have to choose an ordering for the n variables, any of the n factorial orderings. For example, here I chose x2, x3, x1, and then we simply bracket the variables in any meaningful way in an iterated manner so as to obtain, in the end, an element of our ambient vector space. So here's one example, okay, in which I chose to bracket first x2 and x3 together and then with x1. And of course, we span that out and we get a certain linear combination of the monomials that we had before. So the generators, the linear generators of this vector subspace Lie n, well, there are many of those, right? Because when you think about it, you see that what you have to do to construct one of these is to first pick an ordering, so n factorial choices, and then there's a Catalan number of choices for the way in which you can put parentheses around pairs of these elements. So there are many of those elements, but it turns out that, of course, there are many linear relations among these full bracketings. And the vector space that they span, Lien, happens to be of dimension n-1 factorial. For example, when we have 3 letters for Li3, the space is of dimension 2. And here I'm showing a particular pair of full bracketings that spans this vector subspace. This is called the Dinking basis. I'll say a word about this a bit later. For now, I'm just showing you a particular basis of this vector subspace. All right, so we're going to be looking at this vector space Lien. One small thing to point out now is that, of course, this space is just a vector subspace of our ambient algebra. It is not a Lie algebra in the same manner that this other vector space is not an associative algebra. Okay, the connection to Lie algebras and associative algebras I'll make a bit later. For now, I'm just focusing on these 2 vector spaces, pair n and Lien. Okay, so now I'm going to start from a completely separate point. Let's set these 2 spaces aside for a second, and let's consider this other object. It's an object that arises frequently in combinatorics and parts of mathematics, which is the lattice of partitions of the set n. This is the set with n elements 1 through n. And I'm just looking at all ways of partitioning that set into these joint subsets. So for example, at the top here, I drew the partition into singleton blocks. So the 4 elements, so n is 4 in this picture, and the 4 elements have been split into blocks of size 1. But at the very bottom, what I have is the partition into 1 block. And in between, you have all other partitions of the set of this set of 4 elements. And I'm viewing this as a partial order in which the order is refinement. So to move from one partition up in this order, what I am allowed to do is to split any of the blocks of this partition into finer pieces. So for example, to go from this one to that one, what I did is I split the block 1, 3 into 2 pieces. All right, and the object that we obtain is a lattice. It's not just a partial order, but a lattice. It is called the lattice of partitions of n. And I want to look at a geometric object associated to this poset, a simplicial complex, whose simplices are the chains in this poset. So to any poset, you can associate this topological space, and then you can compute its homology. And this is what I want to do that here. In this particular case, when n is 4, well, what you have to do is, first of all, you have to drop the top and the bottom and just look at the piece in between. And in this case, when n is 4, you see that this piece, well, it's basically just a one-dimensional object. It's just a graph. So this topological space that I was alluding to, in this case, when n is 4, is a one-dimensional simplicial complex. It is just a graph. And I'm looking at the homology of that graph. So I'm looking at the number of cycles, independent cycles, that constitute that graph. For example, here is one cycle. If I go this way, and maybe I can return to where I started, and you see that I have a cycle consisting of 6 edges. Well, so it is a fact that the dimension of a certain homology group of this space is n-1 factorial. In this case, n is 4. So the homology group that I should be looking at, so it turns out that this space is always of dimension n-3. In this case, n-3 is 1. We have a one-dimensional space. And this homology group that I should be looking at, that I'm denoting by h top, is really the one at the top dimension. So when n is 4, this is h1. Okay, it's always h sub n-3, the n-3 homology group of the order complex of this poset. And the dimension is the same as the dimension of the space Lien that we had on the first slide. There's another common feature to these 2 vector spaces. The space Lien that we had before, defined purely algebraically, and this space defined topologically out of a combinatorial object. They have the same dimension, but they also are, both of them, representations of the symmetric group, right? Because clearly here Sn acts as by permuting the labels, in this case S4. And in the previous case, there was an action of Sn as well, right? If we quickly go back, per n is of course the regular representation of Sn. I can permute here I can act by permuting the variables. And that action leaves this subspace invariant. So Lien is also a representation of the symmetric group. These two representations not only have the same dimension, but in fact, they are isomorphic. And this is a theorem that we like to call the Joyal, Klyachko, Stanley theorem, which states that these two representations are isomorphic after you tensor one of them with the signed representation of Sn. Okay, so this is a one-dimensional representation, doesn't change the dimension, but when you when you tensor with it, you actually get an isomorphism of symmetric group representations. So Lien is the space we had before, which is often called the n-linear part of the Friedrich algebra. This is just a name. I'll connect to Friedrich algebras a bit later. And this is the homology, the top homology of the partition lattice. So this is a result with a somewhat long history. I'll just tell you briefly a couple of things. Stanley computed the character of the representation of the symmetric group on the homology of the partition lattice using ideas of Hanlon. Separately, and before, Klyachko had computed the character of Lien as a representation of Sn. And at some point, not in the paper of Stanley, but at some point soon after, it was realized that those two characters were the same, up to tensoring with the signed representation, so that the two representations were isomorphic. That might have been observed first by Joyal, but I am not sure. In any case, what Joyal did in his work a few years later was to construct an explicit, well, to come up with a direct proof of this isomorphism without resorting to the separate calculations of the two characters. Joyal employed his theory of species to obtain this result. And then this became the beginnings of a small chapter within algebraic combinatorics pertaining to the study of homology representations and also to the study of the Friedrich algebra. So there is a small chapter in algebraic combinatorics about the combinatorics of the Friedrich algebra. Some of the references that are of that kind are here. Another standard reference for the study of the combinatorial study of the Friedrich algebra is a book by Rautenauer called Friedrich algebras. But of course, the study of the combinatorial aspects of the Friedrich algebra is a very old subject, and I'm going to review some aspects in a second. But first, I want to tell you where am I going with all this. The goal for my talk is to justify this claim, or at least this is one door into what we do with Mahajan, to pick this result of Joyal, Klyachko, and Stanley as a way to access the things that we've been doing. So I want to explain this claim that this theorem that we just stated can be seen as a statement about the braid hyperplane arrangement. So the plan then will be to discuss hyperplane arrangements, and in particular the braid arrangement, and to explain this claim. And if I get to do that, I'll be happy. Really what we do is to generalize this theorem to the setting of all real hyperplane arrangements. Not only we generalize that theorem, but many other classical facts about Friedrich algebras. Okay, so the talk will consist of one part in which I go over classical facts about Friedrich algebras. Many of you may be familiar with those. And another part in which I try to explain how they can be extended to a new setting involving a geometric ingredient, and that is an ingredient of a hyperplane arrangement. So that's the plan. But for now, then, what I'm going to do is list a number of classical results that we are able to extend. But eventually, we'll be able to do that in a second part of the talk. So one result that many people are familiar with is this theorem that goes by the name of thinking, spec, and Weber, which involves this operator on our space per n. Remember, this is the space spanned by the fully associative products, the monomials indexed by permutations, right? In which each variable appears exactly once. So I take one of those monomials, and what I do is I bracket them by always choosing the leftmost bracket. So I start by bracketing the last two variables, and then I bracket that with the preceding, and then I continue doing that. So to each monomial, I associate that leftmost bracketing. That defines an operator from the space of all spanned by all full products to itself. And it turns out that this operator, once you normalize it like this, is idempotent. And moreover, the image, well, clearly the elements that you get are inside the space Lien, right? Are particular full bracketings. But it happens that they span. The image is the space of all Lie bracketings. This operator is called the Dinking idempotent. A closely related result is the following. If you now apply this operator, but instead of applying it to all n factorial bracketings, you applied n factorial full products, you apply it only to the products in which the last variable has been fixed. So you make the last variable equal to xn, and you let the other variables vary. You permute all the other n-1 variables. And you do this leftmost bracketing. Then what you get is exactly a basis. Okay, a vector space basis for the space Lien. So this shows very explicitly that the dimension of this space is n-1 factorial, that fact that I stated before. Now we are restating it in more detail. This is one aspect of free algebras that we are able to extend to hyperplane arrangements that will come later. Another aspect, risk criterion so these are all results from the mid-20th century. Risk criterion is the following. What I'm going to do is look at the space per n, and inside it, I'm going to look at particular elements called shuffles. So here I took two monomials, two full products, and I'm shuffling them. The shuffle product, many of you are familiar with, you just take all concatenations of these two sequences in which, so you're allowed to mix them, but the restriction that you have to obey is that these two variables must appear in the same order. In any of these, they must appear in the same order as the one they had originally. And similarly for the variables that you had here, in this case, there's only one. So you see that basically what you're doing in this case is just inserting x1 anywhere along the way between x2 and x3, before, in between, or after. These combinations of monomials that you obtain are called shuffles. You take all the shuffles, they span a subspace of our space of dimension n factorial, the space of proper shuffles. And this criterion of Rie tells us that the space Lien and the space of shuffles are related in this particular manner. One is the orthogonal of the other. And to speak of orthogonality, we should make reference to a particular inner product. And the product that we choose is simply we make the basis of all full products orthonormal. So we are working inside the space of dimension n factorial. It has that distinguished basis. We make that basis orthonormal, as shown in this picture, right? When n is 2, there are two monomials, x1, x2, and x2, x1. And make those two orthonormal. So one is 1, 0, the other one is 0, 1. And then if you compute the shuffle of x1 and x2, well, it's going to be the sum of these two. So the vector 1, 1. If you compute the bracketing, the Lie bracketing, commutator bracket, well, you get this one minus that one. So it is minus 1, 1. And when you draw those two vectors, you observe that they are perpendicular. Well, more generally, the claim is that if you do this for any n, what happens is that Lien is exactly the orthogonal complement of the space of shuffles. So all these criteria that we are discussing, this criterion of Rie, and to an extent, this theorem of Dinking that we mentioned before, are attempts at describing the space Lien in more explicit terms. So it was defined as the space spanned by all Lie bracketings, but there are many alternative characterizations of the space, and that's what's common about all these criteria that I am discussing. So this is one way of describing Lien in a different manner as the orthogonal complement of the space of shuffles. Now, let me arrive at the connection with Lie algebras, right? We've been referring to this space as Lien, but it is not a Lie algebra in any way. What is its connection to Lie algebras, more concretely with free Lie algebras? Well, so the idea is that you have to use those spaces, that sequence of representations of the symmetric groups, as coefficients in the Taylor expansion of a certain functor. So we use them as coefficients to build up this so-called analytic functor. It is a functor from vector spaces to vector spaces called L of V. The image of V is, by definition, let's say, the free Lie algebra on V. And it happens that the free Lie algebra on a vector space V has this expansion as a direct sum of vector spaces of this form, obtained by tensoring V tensor N with Lien, tensoring them as representations of the symmetric group. Sn acts on Lien, and it also acts on V tensor N by permuting the tensor factors. That is the free Lie algebra, and that is the connection with the vector spaces that we've been looking at. So the vector spaces we've been looking at, and that's why this is called the n-linear part of the free Lie algebra, or the multilinear part of the free Lie algebra. Of course, this is there is a parallel statement for free associative algebras. The free associative algebra is a simpler object in a sense. It's just the tensor algebra on V, and that admits the same description involving now the representations, the regular representations of the symmetric group, the spaces per n that we had initially. And of course, then we recover the usual description of the tensor algebra. It'll play a small role in a second, the fact that I am choosing to start this sum when n is 1. So I'm really looking at the free associative non-unital algebra. So I'm dropping the unit, okay? I'm dropping the part of degree 0 from the usual tensor algebra. That's not a big deal, of course, small detail. So the fact that the sequences of representations give rise to functors that realize free algebras of a certain kind, Lie algebras or associative algebras, can be expressed in various ways. These are two equivalent ways of expressing that fact. These two functors are monads, or equivalently, the sequences of representations, well, it's not quite equivalent, but given that the functors have these special forms, then these two statements become equivalent. These functors are monads on the category of vector spaces, or equivalently, these sequences of representations are operads. Those are just names that we do not need for the rest of the talk, okay? What we only need is this connection, and well, we may, now that we've introduced the tensor algebra, have a chance to, say, employ it to describe another criterion involving the free Lie algebra. This is Friedrichs' criterion from the same period of time, which states the following. We had to first observe that the tensor algebra, well, it is an associative algebra. It's the free associative algebra B, but it is also a Hopf algebra under a coproduct that is simply deconcatenation. So you have a tensor and you break it into an initial piece and a terminal piece. It is a Hopf algebra, very well known. And also, it is very well known that the free Lie algebra is the primitive part of that Hopf algebra. And given that I'm choosing to work with the non-unital part of the tensor algebra, I can state this definition of primitive part in the following terms. I can simply say that the free Lie algebra is the kernel of this map. Okay, that's how we want to view it. So are there any comments that anybody would like to make at this point? Or am I allowed to keep going? All right, there's one more aspect of free Lie algebras that I want to mention, involving another classical construction in this field, the Eulerian Idenpotence. So let me very quickly say, now that we touched upon Hopf algebras, let's consider any Hopf algebra of this kind, by which I mean the positive part of a connected Hopf algebra. I do not want to state that in detail, but the tensor algebra is one such. And when I look at when I drop the unit, then I'm looking at the positive part. Okay. Now, given any Hopf algebra, really, if I have two linear maps, linear maps from H to H, I can consider their convolution. The convolution is an operation on the space of maps from H to itself, defined in this manner. You first apply the coproduct, then the tensor product of the two given maps, and then the product, and you're back to a map from H to itself. So this is an operation on the space of maps of this kind that we're going to employ. I'm going to employ it to build this particular map, denoted E1. So it's a map from H to H. And you see, it is an infinite sum consisting of, it's a particular linear combination of convolution powers of the identity. So I employ the convolution to form these powers. This is an associative operation, so I can form powers. And I take convolution powers of the identity, I take this infinite sum, but it turns out that this is well defined under this hypothesis because the identity on the positive part of a connected Hopf algebra, on any given element of that part, is nilpotent. So when you evaluate this at any particular element, this sum turns finite. So this is a well-defined element. And this element is very special. When the Hopf algebra is co-commutative, this element, E1, happens to be idempotent. So we have another idempotent operator coming in. Before we had the dinking idempotent, this is a different operator. It is also idempotent, and it has the same property. Well, it has the property that on any Hopf algebra H of this kind that we're looking at, its image happens to be the primitive part. So these are all basic facts about connected Hopf algebras that I am recalling. In particular, if we apply this to the tensor algebra, which is a Hopf algebra of this kind, and it is co-commutative, well then, according to Friedrichs, the image of this operator should be the Freely algebra, okay? Because the Freely algebra, remember, was the primitive part of the tensor algebra. This is called the first Eulerian idempotent. There are additional higher Eulerian idempotents, which are defined as convolution powers of the first Eulerian idempotent, normalized in a certain manner, divided by k factorial. I'm going to focus on the first Eulerian only. All right, so I believe that concludes my quick tour of combinatorial aspects of classical aspects of Freely algebras. And I move now to hyperplane arrangements, where I have to introduce a few still basic constructions and ideas so that I can tell you what we do beyond what's known. Okay, let's see how this goes. So let's set all that aside for a couple of minutes. I'm starting anew here. So we're going to work in a finite dimensional real vector space V that's fixed. Nothing to do with the vector space V that was appearing just before. This is an ambient vector space where we're going to be picking hyperplanes. So I'm going to pick a finite set of hyperplanes in V. Hyperplanes meaning codimension 1 vector subspaces. Okay, so I'm not going to be taking affine hyperplanes. They're always going to be linear hyperplanes going through the origin, codimension 1 subspaces. And I pick any finite set of those. That's called a hyperplane arrangement. And I want to do constructions starting from that data. So the main two things that I want to associate to that hyperplane arrangement is two sets denoted by sigma and pi, the set of faces and the set of flats. So let me tell you quickly what those are in a specific example. So in this example, the ambient space V is the plane, just a two-dimensional real vector space. And the hyperplane arrangement is this set of 3 lines through the origin. So here's the origin. And I just took 3 lines through the origin, okay? I want to tell you what faces and flats are in this example. So the faces are always convex cones, and they are defined roughly by intersecting hyper half spaces defined by the hyperplanes in my arrangement. So what are those cones here? Well, the 6 cones that you see here, those are particular faces, but there are more. So the rays are also faces. So these are lower dimensional cones. So these 6 rays are also among the faces, are elements of my set sigma, and the origin itself, where all the hyperplanes intersect, that's also a face. That's why there are 13, okay? 6 chambers, so these are called chambers. The top dimensional faces are called chambers. The 6 rays and the origin. What are the flats? The flats are simply intersections of the hyperplanes. So for the faces, we use half spaces. For the flats, we intersect the hyperplanes themselves. So I pick any subset of the hyperplanes and I intersect them. That gives me a particular subspace, and that subspace is called a flat. So in this case, because I only had 3 lines through the origin, there isn't too much I can do in terms of intersections. So what I can do is, well, say intersect 2 of them, I'm going to get the origin, or just pick one of them. So each of the lines is also a flat, or take none of them and intersect them, meaning I get the ambient space when I take the empty intersection. So what are the 5 flats? The ambient space, that's one flat, the top flat. Then I have the 3 lines, and then I have the origin. So the origin is the only object that is at the same time a face and a flat. Okay, so starting from 3 lines, that's the arrangement. I build 2 sets, the set of faces and the set of flats. Everything is finite here. All right, now let's see what kind of structure these 2 sets carry. First of all, they are partial orders, posets. They can be partially ordered by inclusion, because the elements are subsets of the ambient vector space, so we can order them by inclusion. It is important to mention this fact that there is a map that connects the 2 sets called the support map. Every face is supported on a flat. For example, this ray is supported on this line. Okay, so that would be the support of this face. So the support of a face is the smallest flat containing the face. It is simply the vector subspace spanned by the flat, by the face. The faces are not vector subspaces. The faces are cones. The flats are vector subspaces. And we have the support map linking one to the other, and this map preserves the order, because the order is defined in both cases as inclusion. So here I'm drawing for you the 2 posets that we're looking at, the poset of faces, so this would be sigma, and the poset of flats, this would be pi. At the top here of the poset of faces, you see the 6 chambers. Here you would see the 6 rays. The 6 chambers all have the same support, namely the top flat, because they are supported on the whole plane. And the 6 rays, well, they are supported on the 3 lines. So the support map preserves the order and preserves the rank of these 2 graded posets. Okay, another important ingredient is the Tits product. These 2 sets are not only partial orders, but in fact they are monoids, and this is a crucial structure for everything we do. The set of faces is a monoid under an operation that we like to call the Tits product, because it originated in a different context, somewhat related, but different context, the context of buildings, the big theory of buildings of Jack Tits. That's where this product, or at least it's one of the sources for this operation. And I want to tell you quickly what it is, because it's very easy to understand in terms of pictures. So what is it I'm trying to do? I'm trying to convince you that on the set of faces of any arrangement, there is an operation that is associative and has a unit. So I can multiply 2 faces, get a 3rd face, and I can do that in a manner that is associative and unital. So what do I do? How do I multiply a face F, like this ray, by another face G? I can multiply any 2 faces together. I'm picking for this example, these 2. What is F times G? So this is the rule that I have to follow. I have to stand on any point in the relative interior of F. I choose any such point in the relative interior, meaning I cannot choose this point, but any other point on this ray would be fine. Anywhere in the relative interior. And then I look towards any point in the relative interior of G. So I look in that direction, and I move in that direction. I walk towards G. I do not walk all the way towards G, just a small step, positive step, and I see which face I enter as I do that. There will be one first face that I enter when I move from F towards G. And that's the result of the operation. That's one way of defining this operation in geometric terms. That's the product FG. So you see in this picture, this ray times that ray is equal to this chamber. Rays and chambers are all faces. It's an operation on the set of faces sigma. The picture that you see here on the right, so this is a hyperplane arrangement of rank 2. The ambient space is the plane. This is an arrangement of rank 3. This is happening really over here in R3. Showing a picture with planes in R3 is a bit obscuring because you cannot see through the planes. So what we do here is we intersect the planes with a sphere around the origin. So the planes are represented here as great circles, and we can see a little bit better what the faces, the chambers, and so on are. So here's one face. Really, you should think that this is a ray that's stemming from the origin, which is at the center of this sphere, and it's sticking out through this point. Okay, that's F. This face C, well, it's a face defined by intersecting a bunch of half spaces. But everything then can be casted in terms of the sphere instead of in terms of the ambient three-dimensional vector space. So this is a picture of a hyperplane arrangement, even though you don't see hyperplanes. All right, how do we multiply F times C? Well, it's the same. I gave you the rule before. We should follow the same rule, but in terms of the sphere, the rule becomes, well, you walk from F towards C along a geodesic, along a great circle. So you pick a point in the interior of C. So I cannot pick a point here, here, or here. It has to be in the interior. And I walk from F towards C, and I see which face I enter first. And in this case, it is this chamber. So F times C is FC. So are there any questions about how this product works? Because this is regardless of anything else that I'll try to say, this is a useful basic notion that many of you might have seen or might not have seen. And it's something useful to draw from my talk, I think. Or at least you have to take my word for that fact, that this is a very central structure. I'll make the case for that. Sometimes people have questions about how the product works. That's why I'm trying to stop and seeing if anybody wants to say anything. For example, sometimes people wonder, well, how do I multiply this face by that face? Well, we follow the rule I gave. So you pick a point here, you pick a point there, and you walk from this one towards that one, and you see what happens? You stay where you were. So let me write something on my screen then. This face is the opposite of F, so I'll denote it F bar. So what we just discussed is that F times F bar is F. Okay, that's one small fact. Another one is what happens if you multiply F times F. Well, you pick a point in F, you pick another point in the relative interior of F, you walk from one to the other, F is convex, so you're going to stay in F. So F times F is F. So this monoid is very special because every element is an idempotent. So this is an example of a band. Monoids with these properties are called bands. And such monoids have a special representation theory. They're the one opposite extreme from groups. They're not at all like groups, but they have other properties, and they have a rich theory, and we make use of that theory. By the way, the fact that this operation is associative is not obvious from the pictures, okay? I didn't draw a picture trying to explain why it is associative because it is not so easy, but it is. There are many ways of seeing that it is associative. Now, this is all a structure, an algebraic structure on the set of faces. Remember, I had the companion set of flats. We have faces and we have flats. Flats are a bit simpler because they just involve intersections of hyperplanes. Is there a parallel to this structure on the set of flats? Well, yes, the set of flats is a commutative monoid because, in fact, as I mentioned, it's a lattice, right? Simply because it is closed under intersections and it has a top element. So it is a lattice. It has a join. It clearly possesses a meet, which is just intersection of flats. But then you can also define a join. The join of two flats is the intersection of all the flats that contain those two. And I want to view this set as a monoid under the join operation of the lattice. And if you do that, then the support map transforms the Tits product into the join. So the support map is a morphism of monoids. It turns the Tits product into the join of this lattice. In fact, it can be checked that the support map is precisely a Booleanization of this monoid. So this monoid of faces, one way of understanding it is one can view it as a non-commutative version of the lattice of flats. Okay? It is very close to being a lattice because it satisfies this property that every element is idempotent. This is a property that is, of course, satisfied by lattices when you view them as monoids, because the operation is the join. That operation remains true at the level of the Tits monoid, the monoid of faces. What ceases to be true when you go from flats to faces is that the operation is, the commutativity of the operation ceases to be true. The operation is no longer commutative when you look at sigma of A, the set of faces. But roughly, one can think of this as a non-commutative lattice of sorts. All right, there's one more ingredient, geometric ingredient, that I need to discuss before I can tell you how we extend concepts about the Free Lie algebra to the setting of hyperplane arrangements. And for that, I need the notion of Loon. Chambers we've been discussing. Chambers are those faces of top dimension. So on this spherical representation, the faces are those regions, right, of top dimension. So in this case, the faces are the vertices that you see here, the edges that you see, all those are faces, and these chambers. And of course, there is also the central. When you go to the sphere, you lose sight of the central face, the origin. That's also there. You have to keep track. It becomes the empty face on the sphere. You have to keep track of that. All right, gamma is the set of chambers. If you multiply a face by a chamber, you always get another chamber. When you multiply a face by a chamber, you put the chamber on the right, you always get another chamber. So it is a left ideal. The set of chambers is a left ideal in this monoid. Now what I'm going to do is fix a face and a chamber, the chamber bigger than the face. As in this example, I fix a face, F, in this case, this point, this vertex, and this chamber that contains the face. I fix those two, and then I look at all solutions in my monoid to this equation, all solutions C to this equation. F and D are fixed, C is what's varying. We've been saying this monoid is really far from being a group. So this equation in the monoid, in principle, can have any number of solutions. In a group, of course, C would be uniquely determined, but here this is not at all the case. It always has some solutions because D itself is one of the solutions to this equation, but there are many others. So what do the solutions look like when you picture them on a sphere? Well, they look like loons, loon sectors, as shown in these pictures. So for example, in this case, the chambers C that satisfy this property that are solutions to this equation are D itself, and then this other chamber, and then that chamber, because you see that if you walk from F to this chamber, say, the first one you're going to enter is D. That is expressing this fact that F times C is equal to D. So this loon goes from this vertex all the way to the antipodal vertex on the sphere. Okay, and that's the set of solutions. Here, when F is now an edge, and this chamber that contains the edge, what you get is the hemisphere that contains F on the equator, and the hemisphere that contains D. So those are examples of loons. Loons play a central role in what we do. And here is how we use them for the purposes that we have at hand here today, which is the definition of a space Lie of A attached to any real hyperplane arrangement. So I have my hyperplane arrangement that has been fixed. I'm also now going to fix a field. I'm going to be taking linear combinations of these objects, elements of these sets that we have. I'm going to look at the subspace of all chambers, the vector space spanned by all chambers. So the set of chambers, that's just a set. But I take all formal linear combinations of chambers. And in that vector space, I consider elements. So this is a formal linear combination of chambers, satisfying a bunch of linear equations. And here are the equations. For each loon in the arrangement, the sum of the coefficients of the chambers in the loon has to be 0. So that's a system of equations imposed on elements of the vector space formally spanned by, freely spanned by the chambers. So I impose those relations for all non-trivial loons. The non-trivial loons are those that contain more than one chamber. And I want to call that space Lie of A, and I want to give you reasons for that. So the very first thing I should do is to explain how this definition recovers the definition of the space Lie, the multilinear part of the Lie algebra that we had at the beginning of the talk. So for that, the arrangement that we have to choose is the braid arrangement. The braid arrangement is an arrangement of hyperplanes in Rn consisting of the diagonal hyperplanes, where you set two variables equal to each other, xi equal to xj, I different from j. That's the famous braid arrangement. And the combinatorics of this arrangement are very explicit. One can describe faces, flats, and all the objects we discussed in very explicit combinatorial terms. So a face is going to be indexed by an ordered partition of n. So a face is a set of this sort, where when you think about what you're doing when defining faces, which is imposing inequalities defined by these half spaces, well, you get sets of this kind where what you are saying is, well, the variable x1 is more than the variable x2, and the variable x2 is equal to the variable x3, all sorts of things like that. Those are faces. So all that information is captured simply by an ordered partition, meaning I have put 2 and 3 in one block, and I have declared that the element 1 should come before 2 and 3. And that captures the same information or determines this set. Here's the braid arrangement when n is 3. There are 3 hyperplanes when n is 3, three diagonal hyperplanes, x1 equal to x2, x2 equal to x3, and x1 equal to x3. The hyperplanes, of course, are planes in R3 in this case. Those 3 planes intersect on a line, the diagonal, where all the variables are equal, x1 equal to x2 equal to x3, which is not shown here. On this picture, that line would be perpendicular to the screen through the center. So the planes show on this picture as lines. The rest of the information is irrelevant. And the chambers you see are indexed by ordered partitions into singletons. Those are the same thing as permutations. The other faces are indexed by ordered partitions into fewer blocks, into thicker blocks than just singletons, all the way to the central face, which is the partition into one block. The flats are in bijection with partitions where you ignore the order. For example, these two rays, they have the same support, right? They lie on the same flat. They span the same flat. And you see that what they have in common is that as partitions, they only differ in the order. The blocks are the same, but they are ordered differently. One comes before the other. So combinatorially, the support map is simply the map from ordered partitions to unordered partitions, which forgets the order. So the combinatorics is very explicit. And I'm not going to torture you too much with the combinatorics, just try to hang in for a few seconds with this till I can make the final connection with the Lie algebra. The Tits product, which is the main ingredient, also has a combinatorial description. It's simply lexicographic refinement. But we don't need to dwell on that for too long. Here's what the chambers are, the loons are. So you pick a face like this one, at this vertex, which is an ordered partition, and you pick a chamber that contains it, like this one. And that should be a finer ordered partition, right? So what you have to do is split this block into singletons. So what are the chambers that constitute the loon defined by this face and this chamber, the loon defined by that pair? So the loon is shown here fully, going from this vertex to its antipodal. So what are the chambers that appear in that loon? Well, it's very easy to see from the explicit description of the arrangement that the chambers that appear here are precisely the shuffles of these two blocks, where the blocks are ordered as prescribed by D. So what I have to do is shuffle 2 with 1, 3, 4 in that order. And then I'll get, you see the 1, 3, and 4 are always in that order in these 4 chambers, in the same order as they were here originally. So those are the shuffles that we discussed before. So the loons are really the shuffles. When you look at the chambers that constitute a loon, well, they are shuffles. And the bottom line of all this is that when you analyze the definition that we gave of Lie for the braid arrangement, remember there was one equation for each loon, and what you had to say is that coefficients add up to 0. The coefficients of these loons add up to 0. That's exactly the orthogonality in risk criterion. So our definition recovers the classical definition of Lie from this perspective, thanks to Rie's criterion. So that's the connection between our definition and the classical free Lie algebra. But now that we have this definition, I'm going to say more about that, but now that we have this definition, we can explore what this gives for other arrangements beyond the braid arrangement. And then we get objects that are not directly related to the free Lie algebra anymore, okay? But objects that still possess some of the same theory. So for example, if I look at a dihedral arrangement, so in this case, I just took 4 lines instead of 3 in the plane. So what are lunes? Very quickly, to understand Lie, you have to understand lunes. So what are lunes? So I pick a face and I pick a chamber that contains the face. A lune, if you were able to absorb the definition of the Tits product, you will see that the lune is this half plane. The lune defined by this face and that chamber is this half plane. So the condition that you have to enforce is that the coefficients that you put on these 4 chambers add up to 0. So you put A, you put B, C. Once you put D, this D is determined because this sum has to be 0. And then if you move to the next coefficient, you see that because here you have another half plane, the sum of these 4 has to be 0. So you're forced to put in A again here, and then B, C, and D. So everything is determined. The only freedom that you have is for the choice of these first 3 coefficients. So in general, for an arrangement of n lines on the plane, the dimension is n-1. As you see here, you had 4 lines and you had freedom for 3 coefficients. So I should have said before, I went directly to Lie of the braid arrangement, but remember, Lie is defined as a subspace of the space of chambers. The space of chambers for the braid arrangement is the space of permutations, okay? So the connection with the earlier material in the talk is as follows. The space per n, consisting of permutations, those monomials indexed by permutations, that corresponds to the space of chambers. And the space Lie corresponds to that space that we defined, okay? Those special linear combinations of chambers determined by those Loon conditions, zero-sum Loon conditions. A quick look to the Jacobi identity just to see what aspect it takes in this geometric language. So again, I look now at the braid arrangement. The chambers are indexed by permutations. 6 chambers, 6 permutations. So if I want to build a Lie element, according to my recipe with lunes, what I have to do is pick coefficients for the chambers so that along each half plane, the sum of the coefficients is 0. Semi-plane, I should say. So for example, here I chose coefficient 1 on this chamber. Here, by this 1 bar, I mean -1. So I choose 1, -1, 0. And then clearly I have the required condition. Then again, 1, -1, 0. So if I make this choice, the coefficients are such that on any semi-plane, the sum of the 3 coefficients is 0. So this is one element of Lie. And you see here what I do is I just rotate the picture clockwise 1 turn each time. And what I'm getting is 3 different elements of Lie. And I observe that if I add them together, I get 0 because it just happens that the coefficient of this chamber, the coefficients of that chamber add up to 0. So when I form these 3 elements and I form this linear combination, I add them up, I get 0. This is the Jacobi identity. For example, you see that this element, if I write this element explicitly, well, this 1 is the coefficient of 1, 3, 2. This -1 here, this -1 here is the coefficient of 1, 2, 3. This one is the coefficient, this one is the coefficient of 2, 3, 1. And this -1, the final, is the coefficient of 3 to 1. This is simply the expansion of this bracketing. So the Jacobi identity, written in this form, one of the classical ways of writing the Jacobi identity, takes this geometric appearance. Okay, so that's the connection between the combinatorics of Lie brackets and the geometry of the braid arrangement. Now I want to tell you a little bit more about Lie in this general setting. Now, It's 10:54. I don't know if I can go to 11 or if I should be stopping in a minute. Please, somebody can let me know.
Okay, it is up to you.
Okay, I'll try to stop before 11 to give a chance for people to tell me their thoughts. But I do need to tell you a few more things because I haven't succeeded in anything beyond stating definitions. So one thing that we can work on now is connections between this object, Lie, that we have defined for all arrangements, and the algebraic structure of the Tits algebra. So we define the Tits monoid. I can then consider the monoid algebra of that monoid. We call it the Tits algebra. Just form a linear combination of combinations of faces with the product being the Tits product extended linearly. Well, let's bring in the Jacobson radical of that finite dimensional algebra. And the rank of the arrangement, which I've been alluding to before, well, this is a finite dimensional algebra. The Jacobson radical is nilpotent, and it happens that the index of nilpotency is one more than the rank, and the last non-zero power is exactly Lie. So this is another description of Lie that I find very appealing. It is the last non-zero power of the radical. This fact that the index of nilpotency was this number was known, but the description of the last non-zero power as Lie is ours because the definition of Lie is one of the things that we do in our work. Well, as a small consequence, then we get that the dimension of this space is up to assign the value of the Möbius function of the arrangement. I'm not explaining why we can deduce this, but let me just state it as a fact that the dimension for all arrangements, then we can compute the dimension of this space, and it is simply the Möbius function. The Möbius function of the lattice of flats. This is what this means. The Möbius function of the lattice of flats. Every poset has a Möbius function. And here is the value of the Möbius function from the bottom element to the top element. And that gives you the dimension of this space. Eulerian idempotence, we can generalize them employing the Tits algebra. We had the Eulerian idempotence in the classical setting. Remember, that's now viewed as a special case of what we do, the case when the arrangement is the braid arrangement. Can we make sense of all those classical concepts for other hyperplane arrangements? Well, Eulerian idempotence appear as follows. In fact, we have a very complete understanding of Eulerian idempotence that we believe many of these things are even useful or shed some clarity even in the classical case. So the Jacobson radical happens to be the kernel of the support map. So that means that this algebra is the maximal semisimple quotient of this algebra, which is not semisimple. The algebra of this monoid, the Tits monoid, is not semisimple, but the algebra of a lattice is always semisimple. That's a basic fact. And this is commutative and semisimple. So that means that if you're trying to find a complete system of primitive orthogonal idempotence for this non-semisimple algebra, well, you have to pick the primitive orthogonal idempotence of this one, which are uniquely determined and given to you very explicitly because this is a lattice. And you have to find a section of this map, an algebra section, which always exists, and lift those idempotents. So in particular, the complete systems of primitive orthogonal idempotence for this algebra are indexed by flats. I'm saying that a bit quickly, but that is true. And here's how we can make the connection with Eulerian idempotence. You pick any such system. It's not unique, but you pick any such system, complete system of primitive orthogonal idempotence for the Tits algebra. The elements are indexed by flats. You pick the one indexed by the minimum flat, the origin in our pictures. That idempotent indexed by that flat has this property that when you act with it on the space of chambers, you get Lie. Remember, the space of chambers is an ideal in the Tits algebra. So when I act with it, with an element of the Tits algebra, I will stay within this space. The point is that if I act with this idempotent, I get this special subspace, Lie. So this is another description of Lie. There's more than can be said here. If you use the other elements of the complete system, well, then you're connecting with the higher Eulerian idempotence that I didn't mention. Thinking also has a beautiful generalization. So maybe let me say that and finish. You have to pick your arrangement and pick any generic hyperplane for the arrangement. And that splits the set of faces into two. You look at the faces fully contained on one side, and you pick coefficients 1 or -1, depending on the rank for those faces. All other faces you label with 1, and you form this linear with 0, and you form this linear combination of faces. This is an element of the Tits algebra. It is associated to the choice of a generic hyperplane in the arrangement. That element is an idempotent in the Tits algebra, and again, it projects onto Lie. When you do this for the braid arrangement and you make a suitable choice of generic hyperplanes, you end up building the classical Dinking idempotent. So there's a lot of nice connections between the geometry of arrangements and the classical theory of free Lie algebras. The theorem that I chose to start from, the Joyal, Klyachko, Stanley, holds for all arrangements. If you take the homology of the lattice of flats, for the braid arrangement, the lattice of flats is the partition lattice. And you tensor with a certain one-dimensional space that I don't want to describe, well, you get a space that is isomorphic to Lie of A that we define. And this isomorphism is natural in A. So when you specialize to the braid arrangement, you get an isomorphism of representations of the symmetric group. Okay, so I should stop here. So thanks a lot for your attention.
Thank you, Professor Aguiar. And now, as usual, I would like to hear whether there are some questions, some comments. Are there any questions?
Maybe it went a little fast or didn't hit the right chord, but the slides, maybe I can make them available to anybody who's interested, and I'll be happy to chat with anybody later if that's the case.
Okay, then, if there are no questions, let us thank Professor Aguiar once again.
Thank you.
And let me recall that there is another talk starting in 58 minutes, the same link. The talk will be given by Irina Kashuba, and the title is On the Free Jordan Algebra. So it starts at 2 p.m. Sao Paulo time. That is in 58 minutes. So now we will have for some of us it will be lunch break, for some other colleagues it will be coffee or tea, but you decide. So we resume in less than 1 hour. And let me recall that next week we'll have another talk. It is at the usual time, 2 p.m. Sao Paulo time, by Vladimir Sokolov from the Federal University of ABC in Brazil. He is going to talk about non-abelian for some brackets on projective spaces. I will recall this once again after the next talk. Thank you very much.
Will the next talk be available? Will be recorded? Because I had to leave now to teach, but
as usual, the talks are recorded and then they are put on the web page of the seminar.
Okay.
Okay. Thank you, Marcelo.
Thank you.
Bye-bye.
Goodbye.